二教的东西结束哦。那今天我其实跟大家讲那 deep learning 在这 ASR 里面的一些进程 ，OK， 因为大家学了 HMM、GMM，那 HMM、GMM 大概到2012年、15左右都还有一点点 mainstream，OK，那后来在 deep learning 开始起来之后，就把这个技术把 integrate 到进来。那我会跟大家稍微分享一下，在初期这个引入的过程中，大概是长是什么样子。OK，然后我们大概就做点简单的 overview，那就完成这堂课。OK，so again we'll do this deep learning for audio. Right, so I think I can skip this because few people probably already know the main. There are multiple research topics around speech that will require deep learning. I think automatic speech recognition is the one we talk about. Okay, so I skip all this. Okay, so the Hitler-Markov model again starts in 1970s all the way to 1980s, and then I guess these are the plots that you are very familiar with, right? So again, your HMM decoding decodes through the features and see okay which are the most likely sequence, and you utilize this kind of stuff as a way to do speech recognition. All right, so we'll talk about that later. One of the first things that deep learning has appeared is basically, instead of taking the output probability to be the Gaussian mixture model, it uses a neural network, okay, taking feature input as, let's say MFCC or filter bank as input to a set of deep neural network to be able to generate the probability, omission probability, and that omission probability is going to combine into the original HMM by turbine decoding process, and that sort of starts our deep learning approaches for ASR. We'll talk about that in a little bit. So anyway, so the ASR system, we know, finding the most probable word sequence given the observation. Okay, P of A given W, we usually call an acoustic model. P of W, we call a language model. Okay, training, we find the parameters for acoustic and language model usually separately. Acoustic model are done on speech corpus, so it requires speech waveforms and annotated transcription. Language model, basically there's some extra data from the web, from the anything corpus thing. Okay, so again, language model we know, okay, the N-gram language model that we all learned. Again, it has been later switched to recurrent neural network, okay, because it has very similar flavor. We'll talk a little bit more about this again in the later slides. Okay, so I think this is an important slide, just to keep this in mind. Okay, let's look at the entire flow of the automatic speech recognition system again. Okay, speech audio, that's time signal. Okay, you do some feature extraction, and you get the feature frames. Okay, we usually operationally do this deterministically. Okay, meaning these are basically using MMCCs. Okay, so the probability of the audio given the observation, right? So again, we can think about if it's deterministic, okay, this could also be probabilistic. Okay, this is now deterministic where we learn taking the signals into features. Okay, now for every features, we'll do a classification on the probability of all given Q, right? When I know which states that's in, okay, for a particular acoustic model, I want to see the probability of me seeing that observation, right? Again, then once you have the sequence of state, you have probability of Q given L. So these are sequence of sequence model give you a set of phonemes, okay? Now repeat, you have signals, okay, and you do feature extraction. Every frame what you're doing is actually trying to find which state of a sequence model. Okay, what's the probability of that sequence model it is. Then you have a sequence model that gives you the probability of that particular phoneme sequence. Okay, then you read up a dictionary. Okay, that gives you the probability of word given that lexicon given that essentially this kind of word phoneme. So you have another lexical model that gives you, taking the sequence of phoneme, map them into words. Then you have another set of language model that take the word into a sequence of words that become sentences. Okay, in ASR system, effectively we're taking this speech audio, okay, all the way to a sentence, okay, a set of word sequence. Okay. In an HMM-GMM model, we say this is deterministic, so we use MFCC. We say this entire thing is called a Hitler-Markov model, okay, with Gaussian mixture model to do this thing, okay. Hitler-Markov model to do a sequence to find the best sequence. using Gaussian measure model to say, okay, what's the probability of me when seeing that observation when I'm in a particular state of that hydromorphic model. Take this as HMM GMM. Okay, then we learn those things in the acoustic model. We use a fixed dictionary, okay, meaning deterministic. Somebody give you a dictionary, say, okay, all these things map together to a word. Okay, this phonetic sequence to a word. Okay, this is called lexicon. Okay, and then it could be probabilistic. Okay, then it also can be deterministic. Okay, and finally, you say have a language model that can reevaluate the thing that you just done. Okay, and then finally find the synthesis. Okay, let's think about the entire pipelines of ASR as this kind of process. Okay, so we know usually, okay, speech audio to features are deterministic. They don't have to be deterministic. There are actually work that trying to learn the feature extraction in a probabilistic sense. Okay, but for all practical purposes, okay, and even the current modern state of the art, we say this speech audio time waveform to features, usually they are done with the deterministic rule, usually through a set of signal process. Okay. Okay, again, these are the feature extractor, but like I said, it doesn't have to be deterministic like MFCCs and all those Fourier transform. It could be something like a learnable feature map. Okay, so skip this. And the second part is the lexical model. Okay, the lexical model. In your lab or in our entire courses, we treat them as deterministic, right? Tomato is just a tomato or tomato. Okay, they could all map to the same word tomato, right? Coverage, right? So these two all map to the same coverage. Okay, these are deterministic. Maybe all these things map to that. All these things map to that. Okay. But of course, the mapping can also be deterministic. Okay, not it can be probabilistic. It's a tomato. There's about 55% of chance people say it's tomato. It's a 45% of chance people say it's tomato. Okay, so it depends on the pronunciation of when it's American English, okay, British English, Australian English, okay, or Asian English, whatever. Right? So there's the pronunciation can differ different for a different word. So this can also be probabilistic. When these are probabilistic, okay, then you need to estimate this probability as well. Okay, so if you see people do ASR in terms of finding pronunciation model, okay, it's basically saying it's having a probabilistic lexicon. Okay, it has a dictionary that's probability based. Okay, it's not a single one-to-one mapping or fixed mapping from a phonetic set to word. Okay, again, the GMM and HMM are the ones that we've learned throughout the course. Through this entire pipeline, it takes care of this part. Okay, GMM is per frame. Okay, every frame. Okay, when you are in a particular state of measurement, okay, it gives you some probability, right? It will always say Bj of O, right? At that time t. So at that particular OT, that particular time t, the observation O, we look at if it's coming from the J state, what's that probability? Okay, Gaussian mixture model give me that probability. Right, so we call those kind of approach called frame probability of whether the observation is likely to come from a particular state within HMM. Okay, that is itself is a classification problem. Okay, but when you operationally do that is using GMM. Okay, using GMM to say, okay, I try to estimate the probability of this hydromorphism, that state. When I'm in that state, I have a mixture of Gaussian to give me the probability of me seeing an observation. Okay, so we call that kind of approach is a frame classification approach. Okay, now once you know how likely, if you assign a probability to every frame, how likely is coming from a particular state, then you try to do what's the most likely state sequences that's done on HMMs. Okay, we call the sequence model. Okay, you actually see, okay, what are the actual most probable or likely, okay, sequence transition. Okay, that sequence transition now operationally we do that using HMMs. Okay, so this is the HMM GMM model that we learned the entire course now in these courses. Okay, so I can skip this. I think these people somewhat know already. So we have the observation sequence. You have a state sequence. Okay, the observation is D1, right, particular one OT, let's look at the probability of this observation mission probability. And this probability is now being captured using Gaussian mission model. Okay, this transitional sequence state is being captured by HMM. Okay, so HMM plus GMM are the entire structures of the ASR system that we build upon those two blocks, frame classification and sequence model. Okay, I'll briefly mention this. I won't go into details. When you actually implement an ASR system, usually people don't do it per phoneme only. They do it for what we call the context-dependent model. So your phoneme will look at the previous or the after the phoneme that come before and phoneme come after, and those three things combined into a new unit of phoneme. Okay. So because we know a particular phoneme will sound differently if a phoneme come beforehand and afterwards. So not all phonemes sound the same when in different contexts. So people would group them by the triphone, right? The phone before and the phone after. They become a new unit. Okay, not a single phone, but the triphone as a unit to build the acoustic model. So again, that's also some of the things that little tricks that people do in ASR. I'll skip this thing. Okay, so we now notice that HMS help us to decode, right, the sequence state. Okay. The frame classification right now is being done on GMM, Gaussian mission. Right, so what you are doing is saying, okay, as HMM rows, okay, every state, okay, when every state that comes in, we can try to compute the probability of observation given a particular state, okay, and that's basically sum over a weighting Gaussian. Okay, we call this probability, and we use this probability combined with the transitional probability, put those two probability into the viterbi decoding where we actually decode the past state sequence. Okay, so that's the frame classification probability that we assign, and the transitional probability we put it together, and those two probability used to do the viterbi decoding in actual and ASR decoding process. So again, keep this picture in mind. That's Gaussian mission model, the thing that we learned. So that's what we call NHM and HMM. Now the first thing that people have done is basically switch this thing. Okay. Instead of using Gaussian mission model, they use deep neural network. Okay, so do frame classification. Okay, then similarly still plug into HMM for the decoding. Okay, so how we do that, we can look at it briefly. Okay, so essentially what we're trying to do here is trying to classify the acoustic feature for state variables, right? We can take the softmax output as a posterior probability of state given observation, right? P of QT given OT, right? So if you think about classification using DNN, taking the features and state, there are three states, becomes a three-class classification. We can learn a deep neural network. Okay, at the final layer, use a softmax. Okay, then the softmax will tell you the probability, okay, of whether the observation T is in one of the Q state. Okay, but we need this observation. We need this probability. Right? This observation probability is B of O given QT, right? B of O given QT is the probability of QT given O, probability of O divided by probability of QT. Okay, probability of QT given O, this can be given by a DNN network. All right, so because you don't just learn directly this as your Gaussian mesh model, right? The Gaussian mesh model say we take this equals to weighted Gaussian distribution. We now say, okay, this equals to this probability. Okay, we take this as the softmax output of a DNN frame-wise classification. So every frame, you take the feature in. Okay, it could be MFCC, it can be showtime Fourier transform. Okay, and you try to learn. Okay, whether I'm gonna predict this is state 1 or state 2 and state 3. Okay, that gives you that probability. Okay, multiplied by P of OT, we can somewhat ignore this because this is the same for all different states. Okay, and divided by probability QT, this is just the prior probability for the states. Okay, we know this from the initial HMM GMM. Sort of HMM GMM initialization, those segmental k-means and those sort of stuff. We have this initial probability. This can be now learned using the network. Okay, so that can be done using a various way. Okay, now when you're into that space, okay, to say I need a classification problem to take feature in, okay, to classify one of the state out, and what's that network architecture? Okay, It can be multi-layer perceptron, it can be convolution neural network, it can be all sorts of stuff. Okay, if you use Kaldi, it'll ask you to do time delayed neural network. Okay, those basically you can start designing various kind of neural network architecture to perform this thing. Okay, probability of QT given observation. Okay, it's a classification problem. Okay, so there are multiple ways people have done. You can do fully connected networks. Okay, then you might want to pre-train it using supervising on restricted Boltzmann machine, and then you iteratively add layers to make them into very deep networks. Training usually done on maximum cross entropy for frames. You fine tune a little bit for other tricks, but I'm not going into details, but you can imagine it in that entire ASR pipeline, the frame classification part. Okay, originally it was done B of OT. Okay, under a particular state, what's the probability of missing observation? Okay, we now turn that problem into P of QT given O times P of O divided by Q of Q. Okay, so P of QT given O, think about this probability. Okay, this can be operationally defined as the softmax of a multi-class, okay, a DNN network output. So essentially what you're doing is a static classification, a frame-wise classification, taking the feature in, classify which of the states most likely. Okay, that's softmax probability divided by the P of QT. That gives you the B of O T that you originally used in a HMM-based ASR system. Then the rest of them is the same, right? You have the observation probability, you have the transition probability. You still use Bi-Tree decoding to decode everything to do your ASR system. Okay, so that's a sort of a very simple intuitive approach that starts to bring in DNN, okay, deep neural network, into the entire ASR system. Okay, so these are early days when the people start to do this kind of DNN HMM kind of work. Okay, people start to find very quickly and improve classification, and improve world area performance. Okay, so these are basically different databases, and then a number of hours of training set. And you can just simply, it's very simple. Use a deep neural network and then try to